Okay, well, without further ado, I'd like to introduce Dr. Marta Yebra, who's a senior lecturer in Environment and Engineering at ANU. Her research uses space sensors, which can quantify the dryness of the landscape and predict future bushfire severity. So we're really interested to learn more about the issue of bushfire severity and how climate change may be affecting that. Please welcome Dr. Marta Yebra.
Hi, thank you very much for the introduction. Can you all hear me well?
Yes.
Good, thanks.
We can hear you very well, thank you.
Okay, good, good. Yeah, all right, so today what I'm going to talk about is a bit yes, how we are mapping bushfire risk, mainly using remote sensing data because that's my expertise. But I've been also asked to link a bit bushfire risk with climate, and I'm going to do that a bit at the beginning to put everything into context. But having said that, that's not my field of research, so I just going to briefly talk about that. So just to start and put the fires into context, well, we know that flammable vegetation and the prevalence of hot and dry seasons in Australia predispose all these landscapes to burn whenever there is a ignition source. And it's been like that for a very long time. So vegetation and animals are used to cope with fires during certain times of the year that are different in different areas of Australia. And with this, we have always defined very specific fire regimes in Australia. However, we've been seeing that this is changing and the fire seasons are getting longer. And we all know that this year we started having fires in September and in tropical, subtropical rainforests. So forests that regularly don't burn because they are normally too wet to burn. And this is not only happening here in Australia, it's happening around the world. So you may remember a couple of years ago, the Californian fires that were happening in November. So these fires were burning very hot, very late in the year, when people have fires in November in the northern hemisphere. And normally these fires are very low severity and very easy to extinguish. But that was not the case again because the temperatures were hotter and the vegetation was drier. So what are the things that influence the fire behavior and the fire risk? Well, this is the fire triangle that basically explains that in very simple way. So the fire behavior and the fire risk is influenced by three primary factors. First, the weather that drives it, and then the fuel through it burns, and then the topography across it burns. So what happens then? Well, with climate change, of course, we have a direct first order effect in aspects of local weather and climate. And also this has a secondary effect on other aspects that influence the fire. For example, the fuel and the fire behavior itself. So because of this situation, we need to adapt because with the climate change, the situation is getting more difficult. So we have fire seasons that are longer, and therefore there is more competition for resources, and therefore there is a clear need to be more focused on. Hold on, I see if I can. Sorry, yeah. So to see if we can find more effective ways to better mitigate and prepare for these events, and be more focused on prevention and mitigation more than firefighting, because as we have seen during this fire season, these fires are really difficult to extinguish. So now more than ever, we need accurate information about fire behavior and fire risk to fit these screens and provide end users, fire and land managers and emergency managers with accurate and real-time information that can help them to make these decisions. Are we prepared for this? Do we have the information? Well, I'm afraid that we are not very well prepared, because the fire danger rating we are using today is a fire danger rating that was developed in the 60s, as we all know, by MacArthur. And yeah, and it's very limited in the number of variables that it uses to predict fire danger rating. So basically it uses only weather variables: temperature, relative humidity, wind speed, and an approximation of fuel using a drought and rainfall parameter. So fortunately, this is known, and the limitations of this danger rating system are well known, and therefore all governments in Australia in 2017 decided that we needed a new fire danger rating system that would be more comprehensive and would include a lot more input variables. And here we have a list of all those input variables that are considered important for fire risk. And therefore also will incorporate more modern science. There is a lot of science that has been done since the 60s. So the idea will be to incorporate more modern science and more input parameters. So within all this context, my work mainly focused on deriving information about the fuel condition. And that's what I'm going to be focusing the most in my talk today. And basically, when we talk about fuel condition, we talk about basically 3 parameters of the vegetation. First is the structure of that vegetation, the quantity and the load of that fuel or vegetation, and then the moisture content, how dry it is. And these 3 parameters all together determine the flammability of the landscape. And here I have a few pictures to explain this a bit more. For example, if we look at the same place in, let's say, spring and summer, it is obvious that that place in spring is less flammable because there is more moisture content, so the vegetation is greener, and therefore the probability of ignition to go and burn is lower. But if we compare 2 equally dry sites, for example, this one on the left with this one here on the right, they are both equally dry. So we need to include other parameters to see which one has a higher fire risk. And if we look at this one, it has a lot more fuel load. The structure of that fuel is a lot more complex, whereas here there's a lot of fire breaks and more space that acts as a fire break, and therefore the fire risk of this site is lower. So in consequence, is the combination of structure, quantity, and moisture content what makes a comprehensive characterization of fuel condition. So let's start a bit more talking about the live fuel. So why is live fuel that important for fire behavior and risk? Well, there has been quite a few studies that have demonstrated that as the fuel gets drier, the fire spread rate is higher, and the other way around. So when the vegetation has more water, the energy of the fire first needs to be used to evaporate the water that is inside of the leaf, and therefore it takes longer to ignite. And it takes longer to ignite one particle in the fuel bed. It does also take longer to propagate during in that fuel bed. But it has also been demonstrated that the fuel moisture content influence the number of fires and the extent of the fires. There are certain thresholds of fuel moisture content that explain more fires and the larger fires. So when the fuel moisture content gets lower, there is more fires, and those fires are larger. Again, we said that it is not only about fuel moisture content, it's also a combination of fuel structure. And this is an example of a work from some colleagues that concluded that maintaining a greener vegetation around the houses provided additional protections from wildfires. So it was not only about cleaning up vegetation around the property, but also to keep vegetation that was green. For example, here we see in this axis the probability of house loss for 3 different situations that have different, let's say, water content. This is an index that is an indirect measurement of moisture content. So here is water vegetation, this is drier vegetation. And here we have for different percentage of cover trees, so for different percentage of fuel load in that property. So for a 20% of property with an intermediate water content, we have a probability of house loss around here, around 0.5, for example. If we increase the percentage of cover in that buffer around your house, the probability of your house loss is higher. But if at the same time you increase that amount of vegetation, but you also increase the vegetation moisture content, so you plant a vegetation that is more moist, the probability is decreased. The probability of your house to be lost is decreased.
Mm.
So you might be curious to know how you can retrieve fuel moisture content, and I'm a remote sensing expert, so I use satellites. And how can you retrieve fuel moisture content using satellites? I'll try to explain that in simple words. So basically, when you have the sun irradiating some solar radiation, this radiation hits the leaves, and part of that radiation is absorbed in the vegetation, other part is transmitted to other layers in that plant, and other part is reflected back to the sensor. So when the vegetation has a lot of water inside, the absorption is stronger, so there is more energy absorbed, especially in this region of the spectromagnetic electricity, the wavelengths. And then, therefore, there is less energy reflected back to the satellite. And the other way around, if there is less water, there is more reflection. So therefore, the satellite is able to pick up differences in moisture content given the differences in the absorptions done by the water content inside of the plants. So because of the importance and the capability and the opportunities to estimate moisture content with satellite observations, we derived the first continental scale website providing this information using the freely available satellite data. And this is how the website looks like. You have here the link to the website, so you can click and access whenever you want. And basically, you can see the fuel moisture content conditions for any date and any location in Australia. This is an example of the moisture content of Australia just in December. And as you could see, there were a lot of very dry areas in the southeast coast. You can see some areas that are in blue, but those areas are forests that typically have higher moisture content than grasslands in red. But those moisture contents are still around 100% that are considered very low moisture contents for forests. Of course, you can zoom everywhere in Australia, and this is an example of a zoom in the ACT during the Namadgi, the Oral Valley fire. And you could see how dry the vegetation in that area was. So most of these areas are forests, and they have values that reaches the normal values of grasslands, so very, very low values. And I just put this image as a comparison. So this is exactly the same date in 2011. That was a pretty wet year. And you can see that there is a huge change in the landscape condition. So this map also from the website shows how the fuel moisture content was in comparison with the long time series. Well, for climate studies, this is not a long time series, but for satellite data, it is. So here we compare the moisture content conditions of 2019 to 2001 to 2000. Sorry, this should be 18. It's an error here. So as you can see, most of the areas in the southeast coast, again, had fuel moisture contents that were below average. And what I show here in these box plots is the box plots indicate the fuel moisture content of forested areas in the long time series from 2001 to 2018, in comparison with the fuel moisture content conditions of the forest in this fire season in 2019-2020. And as you can see, the fuel moisture content values of the forest in this fire season was a lot lower than the average in the time series. So I said that fuel moisture content is not the whole story. So you also need to know how much fuel it is and what's the structure of that fuel. So this is traditionally this is traditionally done in Australia using a visual assessment that fits into the overall fuel hazards assessment. And as you can imagine, when it comes to do a visual assessment, this is very subjective. So different observers give different values. And therefore, we could use also remote sensing data to give more objective values to these fuel loads and structures. And this is an example of what we call terrestrial LIDAR. It's a little LIDAR that you hold in your hand. And as you walk around the forest, this emits some beams of light that hits the different structures of the forest. And the machine records the time that that light takes to return. And if you do over all the forest, and as you know the velocity of the light, you can retrieve the distance between the objects. And with that, you can recreate a three-dimensional view of the forest. And this is an example of one scan we did in Mulligan's Prats here in the ACT. So once you get the point cloud, you can have very clever automatic algorithms that classify the different elements of the forest. And therefore then you can extract different metrics out of these forest layers. Of course, the limitation of this technique is that it's very local. So by far, it can be applied to the whole Australia. So here, Airborne LIDAR gets a bit better. You can cover larger territories. Here you have an example of a point cloud for the Tesla Tower and the Black Mountain that was collected in 2015. But this data is still a bit expensive to collect, and it is not collected regularly across Australia. So there is a bit of a limitation in terms of deriving fuel load and structure information. But nevertheless, this is a sample of a map we produced for the ACT. And this is specifically the area of Square Rocks a couple of years ago. If you remember this summer, no, the summer before, there was a small fire in the Square Rocks. And what this map shows is the perimeter of that fire, and here the fuel loads of the elevated fuel. So areas in red are areas that have a lot of fuel, very high fuel load, and areas in blue and different blue ranges are areas with lower fuel loads. And these maps are used by the land managers to, for example, locate a site free of trees, so they can bring specialist firefighters in to access the fire, and also to open new trails to get access to the fire. So far, I've been mainly talking about using the remote sensing data to estimate bushfire risk based on fuel moisture condition. But the remote sensing data can also be used to provide useful information during the fire and also post-fire. So during the fire, basically what you are trying to monitor is the lights and the differences in temperature. So you could have some algorithms that can detect active fires and how those fires progress over time. During post-fire, of course, what you are trying to map with the satellite imagery is burn leaves, ashes, and carbon, and also see the reduction in biomass. And with this, the objective is to generate burn area maps and severity maps. And also from those and the difference in biomass reduction, you can also compute the carbon emissions from the fires. And finally, you can use also satellite imagery to map the regeneration of the vegetation. So this is an example of some satellite imagery from a European sensor that is called Sentinel-2 in the area of Batemans Bay in New South Wales at the end of December. And you can see all the active fires and the smoke plume. And here on the right, you can see even the pyrocumulus. So when it comes to detecting active fire, it's very important to have very frequent imagery, of course, because if the fire starts but there is no satellite overflying at that time, the fire is not going to be detected. So one of the advantages for this is the geostationary satellites, because the geostationary satellites look at the same portion of the Earth all the time, and therefore they can take more images than the other satellites that rotate around the Earth. And therefore you can see how this example that is from Imawari 8 hotspots can track the progression of the fire more effectively than MODIS, that is a satellite that only overflies Australia twice a day. So this is an example of other another algorithm we apply to satellite imagery to map the burn extent of some of the fires around Sydney. And with this, you can make an idea of how fast the fire spread and how huge the final burn extent was around this area. In yellow, we are indicating the active fires at the time of the map. This is the same area, but what we are mapping here is fire severity or burn severity. So areas in green are areas that are untouched vegetation or have been burned with very low severity. For example, only surface fires with the canopies untouched. And in redder colors or areas that have been highly affected and burned up to the crown of the trees. So mapping the severity of the fires is very important for many aspects, but one key aspect is also to targeting remediation efforts to protect the water supplies post-fires. Here I just map an example of the Pechey fire in Queensland, where again it burned 2 water reservoirs, and therefore they wanted to start planning remediation activities as soon as possible to avoid the contamination of the water in the catchment. So I just want to almost finalize with a slide summarizing how the 2019-2020 fire season was in terms of the percentage of area burned. And because there has been a lot of discussion whether this season was unprecedented or not. And when it comes to total burn area, as you can see in this bar chart, it was no unprecedented. So the amount of total burnt extent was lower than in average, and there were other seasons that had larger burn areas. But when we break this into different land cover types, we quickly see why this fire season was unprecedented. As we can see, it really impacted forests. So the area of forest that was burned was really unprecedented. It has never been burned before. But of course, there was also a decrease in the tropical woodland that was burned. Mainly probably because of the drought, there was not enough fuel in the inland center Australia to burn. So there was less burns than typically in those areas, whereas in the forest, because the forests were so dry, the area that was burned was higher. And I guess that was the summary I wanted to present today. And I wanted to give a key home message that the increasing the climate change in that is challenging the fire management situation. And of course, we need to have more proactive approach to reduce the likelihood of catastrophic fires. And information as this one that I have presented today can help fire managers in their prescribed burning efforts and also improve awareness of fire hazards and predisposition of firefighting resources.
Thank you very much, Marta. A very interesting presentation there. Lots of very interesting material and pictures. Yes, I imagine there are a few questions. I was surprised by your last comments there. Maybe I got it wrong. You're suggesting that you're saying that the area that was burned overall wasn't as big as previous fires this last season. Am I getting that right?
In terms of total area across Australia, it was below the average. So here we have 2019 in dark green. But in terms of the geography of the fires, it was unprecedented, because if we look at the forest, the area that was burned in 2019 was far higher than ever before. So it's, in total numbers, the area was less than normal, but in terms of the ecosystem that affected, it was highly affecting forest fires.
Yes, it just seemed highly, it was reported quite widely. I thought that it was very, it was the most widespread fires we'd seen, but just overall areas. Anyway, I'll over to other questions.
First question, what is the best way to plot the long-term increase in fire risk for Australia?
Yeah, well, at the moment, we only have, we can only do it with the MacArthur Fire Danger Rating System. So, yeah, based on the long time series of temperature, relative humidity, and wind speed, you could see the trend in the fire danger. That answered your question?
I'll keep going, and doubtless they'll keep coming in. The next one, how do we get a fuel load moisture content of more than 100%?
Yeah, that's a very good question. Yes, and I get that often. It's because I haven't defined what it is. So the fuel moisture content is the water content per dry mass. So if there is a lot, if there is less dry mass than water content, it can go over 100. So it's because it is a relative measurement per dry mass.
Okay, I am really relying just on the wording because I'm so out of my depth. Okay, total area burnt was well below average, but total forest burn was well above. What do we know about total CO2 release compared to other years?
It's being higher. Yeah, I don't have the data to show here, but it's being higher than other years. Yeah, probably because the amount of biomass in a forest is a lot higher than in a savanna, tropical savanna that normally burns. So perhaps that's why the emissions have been higher.
Okay. Oh, This is Rowan's question. Do you think more research and cooperation from the government towards atmospheric research would improve, you know, Australia's potential for moving on climate change?
Well, definitely, yes. I think that's definitely an area that we always need research, and because it affects many other different fields as fires. So it's climate is influencing many aspects of our lives. So yeah, always more research is needed.
Explain, Marta. Catherine's asking all the questions because they've been typed in through the chat on this session. So the questions are coming from lots of different people here.
Mm-hmm. So shall I see the chat? Sorry, what was that? Do you want me to have a look at the questions in the chat?
I'm just looking.
Well,
I'm going to look around for Rowan because he wants to ask a question on PWV and radioactive forcing. So now I'm out in the stratospheric edges of my own understanding. And there's another question about, and gosh, this year we heard so much about Aboriginal or Indigenous burning practices. Would you have any comment on that while I have a look for Rowan on the list?
Yes. Well, I don't do research specifically on that, but I mean, yeah, I think that it's similar like prescribed burn. So we need to burn the landscape to keep it clean. And of course, the traditional ways of burning have been very effective for a very long time. But I guess what is happening now is that we have such a weather and such a dry landscape that even areas that have been burned either traditionally or with farm management, they still burn up to the canopy, yeah, because the canopies are so dry that very easily ignite, even though there is no very high fuel load in the understory.
And Rowan, I found you. There, and you've disappeared again. Oh. Sorry, anybody else with questions? Rowan, I found you.
Throw one that, there's one that Peter's asked that I think could be extended. What's the best way to plot the long-term? The long-term increase in fire risk for Australia? We're all very worried about climate change, and it would be excellent if there was some sort of plot of the severity over the years and how that may be impacted by climate change. Is there any study that would give us a forecast of how things may change?
It does, but mainly only based on, again, the MacArthur fire danger rating system that only consider weather, and therefore it might not be fully realistic because it's missing all the other components that are important when it comes to fire risk, that like the fuel that is obviously related to weather. But yeah, you may not be able to have the full picture because you are missing other components of the fire risk. But there are a few studies that have looked, studies from some colleagues in Fenner, Jeff Curry and Phil Gibbons have published a few examples of how climate change and using projections in temperature and precipitation can affect the fire danger ratings.
Thank you.
Sorry about that, Catherine. And
that's quite all right. I'll let Rowan in, and then we've got another 3 or so. Are you okay with that, Marta?
Yeah.
Great. Rowan, go for it. Oops.
Thank you, Catherine. Yes, it's pretty amazing to see research and satellite detail of that level and resolution. And I'm certainly interested to know if from Marta's knowledge, what level of research that's going on with the Australian government in regards to measurement of PWV, precipitable water vapour, and also whether they do actually much research on radiative forcing. There's when you search for it around the place, you can see a bit around in a few sites and centres, but it's hard to find relevant information for Australia. Thank you.
In terms of radiative forcing, you mean?
Radiative forcing, yeah, in the upper atmosphere, yeah.
Yeah.
Yeah,
I don't know much about that. Yeah, I wouldn't be able to tell you how much research is on that. Yeah, unfortunately.
That's all right. Just interested in feedback. Yeah, thank you.
Yeah, no thanks.
And Dennis has a question.
Yeah, hi, Marta. Back in 1986, one of the prime movers for his approach to Congress was James Hansen and his colleagues' work at NASA, where they applied very early modelling techniques, which have now proven to be pretty good. But one of the things that moved original researchers in Australia, Tom Beer and Graham Pearman, was a graph that showed extreme drought and very dry curves, basically, looking at probability increases. And one of those was really very clear, and in fact the extreme one was almost predictive of what's just happened recently. So my answer is that, my question is, sorry, can you take that sort of information, or is that sort of information in terms of predicting dry times being imported into modelling which predicts how the severity of fires?
It is definitely, yes. There are a few studies that we are finalizing at the moment for the current fire season that demonstrated that yes, the areas that were drier in the landscape were affected with higher fire severity. But this is always a bit different, difficult to give cause effect answer, because of course there is also suppressions activities and other things influencing in the analysis that we cannot account for.
Okay, see.
I'm going to roll two questions here together. Are there different mitigation strategies for different areas? And is the outback any less dry, or is it less dry than the coastal areas?
Yes, I'll answer the second one first. So the outback was dry, and it was so dry that there was no fuel to burn at all. So because there was no growth of the vegetation, so that's why my bar charts saw a decrease in the fire activity, because there was no fuel at all. So it was a decrease because there was no fuel. As I explained, it's a combination of fuel dryness and fuel amount. And the first question was, what was it again? Sorry.
Are there different mitigation strategies for different areas?
Activities. It depends what you call mitigation activities. So most of the way the land managers, as you know, mitigate fire risk is mainly by prescribed burning at the moment. Is probably from the three components that are in the fire triangle, fuel is the only component that they can really work to mitigate fires. So yes, they do prescribe burns that are more or less effective, and there is a big debate around that. But yeah, so yes, the answer is that they are different depending on the areas, because if we talk, for example, about prescribed burns, they do only burn where there is a big fuel load in the understory, and therefore they want to reduce that fuel prior the fire season. Where
Okay, and there's
Well,
one more
right.
which I'll read.
Okay, we'll make this the last one if you like,
Okay.
Catherine.
All right, okay. Has Australia followed up on work of the Soil Science Society of America, where 91% of Oklahoma's largest fires during the growing season broke out when soil moisture dropped below levels that caused plants severe stress? Is the reverse correlation true, in which case a predictive indicator of fire? Marta is nodding. Thank goodness somebody knows what I'm talking about.
Well, I didn't know specifically about that work he mentioned, but yeah, we are definitely looking into soil moisture content and how that relates to fuel moisture content and fire danger. And yes, there is a correlation between fuel moisture content and soil moisture content, with a bit of lack of time depending on which kind of vegetation we are talking about. So yeah, as you can imagine, the response of a forest to a decrease in the soil moisture content is not immediate. So it needs to have a very, the dryness in the soil needs to be there for a very long time period for then the plant to respond to that dryness. But yes, there is good correlation, and both are indicators of the fire danger. Yeah, but when it comes to near real-time observation, the fuel moisture content is a better indicator than the soil moisture content because of this time lag between soil dryness and vegetation response.
Great. Well, I think that's been a wonderful presentation. Thank you for joining us this afternoon to give us that, Marta. I think everybody would be really appreciative, and we'll show our appreciation in a silent way since remotely muted.